Rudder is a device used for steering and maneuvering a vessel. Rudders are generally hydrofoils, which are pivoting on a vertical axis. They are located normally at the stern behind the propeller to steer the ship and help in its maneuvering. The world's oldest depiction of a ship's rudder can be seen on a pottery model of a Chinese ship dating from the 1st century AD. There are three main types of rudders used in commercial ships: balanced rudder, unbalanced rudder, and semi-balanced rudder. Out of these three, unbalanced rudder is now obsolete. A balanced rudder is basically a rudder plate that is fixed to the rudder stock only at the top of the rudder. In other words, the rudder stock or the axis of the rudder does not run down along the span of the rudder. In balanced rudder, the rudder stock is at such a position that 40% of the rudder area is forward of the stock and the remaining is aft of it. The rudder nowadays you see on most of the ships are semi-balanced rudder. The name semi-balanced itself implies that the rudder is partially balanced and partially unbalanced, which allows the steering gear to be lighter and smaller. The top part being unbalanced will help in acting as structural support to the rudder from vertical displacement, and the balanced part will render less torque in swinging the rudder. As a result, a semi-balanced rudder returns to the centerline orientation on its own if the steering gear equipment fails during a turn. To understand the function of a rudder, we need to delve into the mystery of the role of a rudder in a ship. Did you know that rudder does not turn a ship? Yes, you read it right. So how does a ship turn then? And if not the rudder, then what is it that turns a big ship? When the helmsman changes the rudder angle from 0 to some angle towards the starboard, at that very moment, a lift force acts on the rudder. The direction of the lift force is towards the port side. This rudder force, as you can see, is directed along a transverse direction to the ship. In other words, this force will cause the ship to attain a sway velocity towards the port side. It is because of this, a ship will sway slightly to the port when the rudder is turned over to hard starboard. But this sway is so negligible, it is hardly felt. Other than this, the rudder force has another effect on the ship. It creates a moment about the center of the gravity of the ship in the direction as shown. Imagine the size of a rudder in comparison to the size of the ship. The rudder is incomparably smaller to the size of the hull that is to be turned by it. So, how does the rudder turn the ship? When the rudder moment acts about the ship's center of gravity, it slightly changes the ship's orientation by giving it a drift angle. This moment is not large enough to turn the ship to the required heading angle. But all a designer has to do is make sure that the rudder moment is enough to introduce a slight drift angle into the ship's movement. The ship with the drift angle is now moving along the initial direction. But this is not pure surge anymore. You'll see you can make components of the ship's velocity along the surge, which is longitudinal direction, and sway, which is transverse direction. Thus, it is evident that by introducing a drift angle, the rudder has introduced a small surge velocity to the ship. What happens after this is what makes the ship turn. To understand the mystery behind the turning of a ship, let's not focus on the surge velocity here. The prime focus should be on the sway component, because that sway velocity component is what changes the hydrodynamics around the ship's hull to cause it to turn. With a sway velocity towards the port side, the hull sways towards the port. When it does so, it exerts a force on the water particles that are in its port side. The water particle in turn exerts an opposite force on the ship's hull due to the inherent inertia of the water particles. The direction of this inertia force is always opposite to the sway velocity, since inertia force always opposes the motion. So, the ship's hull experiences an inertia force on its hull in the starboard direction. One half, the part of it that acts on the stern of the ship, or inertia force at stern, and the other half acting at the bow, or inertia force at the bow. Now the hull is designed in such a way that sway inertia force at bow is always more than that at the stern. Therefore, the resultant moment is toward the starboard direction, making the ship to turn starboard.